In this lecture here, we're going to start chapter 3, and chapter 3 is about polynomial and rational functions. And so in this first section here, we're going to start with kind of one of the easier polynomial functions, and that's just going to be quadratic functions. So you've heard the term quadratic before, right? So we've talked about quadratic functions. We've defined them in a previous lecture. This is just something that looks like the most simplest one is something that just looks like this. So the squared term. So it's going to be some type of parabolic shape here, these functions. Okay, so what we're going to do here in the objectives of this lecture is, first thing we're going to do is we're going to recognize the characteristics of parabolas. We're going to talk about how you graph parabolas. I believe I have 3 examples for that. So I'm going to show you a lot of different methods for going about this. Then we're going to determine a quadratic function's minimum or maximum value. There's a very simple equation for that. And then the last thing we're going to do is we're going to solve problems involving a quadratic function's minimum or maximum values. And what this is going to be, and this will be the last part here, this is going to be kind of word problems. So max-min word problems. And if you ever, and just as a little bit of a preview, if you ever continue on in your studies of mathematics to go into calculus, pre-calculus, calculus, you'll revisit these type of max-min problems. Okay, so let's go back. Let's first talk about parabolas, okay, in the context of quadratic functions. So first thing we're going to define is what's called the standard form of a quadratic function. So the quadratic function that looks like this, f of x is equal to a, and then in parentheses x minus h squared plus k, and this is where a doesn't equal 0, is what's called the standard form of a quadratic function. So let me just give you an example. So f of x is equal to 2 times x minus 3 squared plus 5, something like this. So notice that the values of a, h, and k are filled with numbers. Okay, so if you have a function of this form here, okay, the graph of this function f is a parabola whose vertex, and so what a vertex is it's the turning point. So when you have a parabola that opens up like this is the vertex, that turning point here. Or if you have a parabola that's like this turning point up here is the vertex. Okay, so the parabola whose vertex is the point hk. So when you look at this standard form here, the h and the k here tell you the turning point of the vertex. So just from this example, we can see the vertex here. This is my h, this is my k. So the vertex has the turning point hk, so this one turns at 5, 3. Now the parabola is symmetric with respect to the line of x is equal to h. So this is what's called the, if you look back here, it's what's called the axis of symmetry. So it goes right through the vertex. And what it means, if you were to cut the line in half, right there, you'd fold it on top of each other. They'd be mirror images of each other. So axis of symmetry. So it's the line x, so it's the vertical line x is equal to h. So in this case here, it's x is equal to 3. And so if next thing you do is you look at the value a in front of the parentheses here. If a is greater than 0, the parabola opens upward. And if a is less than 0, so if a is negative, the parabola opens downward. So looking here, so since a is greater than 0, so we see here that 2 is greater than 0. This quadratic function here, the parabola of it, opens upward. So if you were to sketch the graph of this function right here, it would look something like this, okay? All right, so let's now talk about how you would go about graphing these quadratic functions. Okay, so if you have a function that's in standard form, okay, you're going to follow these 5 steps. So if you want to graph f of x is equal to a, and then in parentheses x minus h squared plus k, the first thing you're going to do you're going to determine whether the parabola opens upward or downwards. So you're going to look at the value of a. If a is greater than 0, it opens upward, and if a is less than 0, it opens downward. All right, so let's as I go through these 5 steps, let's do an example just so you could see. So here's the first example. Graph the quadratic function f of x is equal to negative, and then in parentheses, x minus 1 squared plus 4. Okay, so the first thing you're going to do, opens upward or downward. All right, so notice how there's no value in front of here, so there's really an invisible 1 here. So negative 1. So since a is less than 0, we're seeing here that negative 1 is less than 0. This opens downward. Okay, great. So, I know that as I sketch this, it's going to look like this. Okay, that's the first thing it tells me. It's going to open downward. All right, the second thing you're going to do is you're going to determine the vertex of the parabola. And the vertex is HK. Okay. So look here. This is my h, so it's minus h, so I got minus 1. So my h is 1, and this is my k. My k is 4. So the vertex occurs at the point 1, 4. Okay, so that's going to be the point, my turning point of the graph. The next thing you're going to do is you're going to find any x-intercept, so where it crosses the x-axis. Okay, you're going to solve this by solving f of x is equal to 0. Okay, so the function's real zeros, so if you get solutions that are real numbers, okay, are their x-intercepts. So you find x-intercepts by solving f of x is equal to 0. So look, I'm going to take this expression, minus x minus 1 quantity squared plus 4. I'm going to set it equal to 0. First thing I'm going to do is I'm going to subtract the 4 over. Notice how negative, negative, I'm going to divide by a negative, and I get x minus 1 squared is equal to 4. So now what I'm going to do is I'm going to take the square root to solve. Well, when you take a square root to solve, you get 2 solutions. You get plus or minus square root of 4 is 2. So look, you have 2 x-intercepts here. I'm going to add the 1 over. So you get x is equal to 1 plus or minus 2. So one x-intercept occurs when x is equal to 1 plus 2. So is that 3? So that's the point 3, 0. And another one happens when you get x is equal to 1 minus 2, which is minus 1. So another one occurs at minus 1, 0. Okay, so just so we're clear here, you have 2, because when you took the square root to solve, you got that plus or minus. You have 2 x-intercepts at the points 3, 0 and minus 1, 0. Well, this is great, right? Like, look what I know here. I know where its turning point is. I know the vertex. And then I know 2 other points, the 2 x-intercepts. So going back, the next thing you're going to do is you're going to find the y-intercept. So that occurs when x is equal to 0. So find y-intercept. Okay, which is going to occur at 0, f of 0. So I'm going to take 0 and plug this in, right? Well, 0 minus 1 is minus 1. Minus 1 squared is 1. So minus 1 plus 4, because you still have that negative out front, don't forget that, is 3. So the y-intercept here is going to occur at the point 0, 3. Then the fifth thing you're going to do, the final thing, is you're going to plot the intercepts, the vertex, and any additional points as necessary, only if you need them. And then you're going to connect the dots or sketch through the dots a smooth curve that is shaped like a bowl or an inverted bowl. Okay, so look, we know it opens downward. Let's plot the vertex 1, comma 4. So 1, 4, here's the vertex. The intercepts 3, comma 0 and negative 1, comma 0. So here's negative 1, comma 0, 3, comma 0. Let's plot the y-intercept 0, 3. And look, do you notice how, if it helps to see this, here's the axis of symmetry going through the vertex. So this point would have a mirror image on the other side here. And look, you can see, so plot the points. And then smooth curve. And forgive my rough curve here. Actually, this one looks pretty good, actually. And there you go. You plotted the vertex, you found the intercepts, and then you got an extra point or two if you needed it. And you can see whoosh, right there. Perfectly done. Very, very easy. Okay. Now here's the thing. Not all parabolas are like this. Okay. So, not everything what I mean by are like this are in this standard form here. Okay. So what if it looks like just a normal quadratic function like this, ax squared plus bx plus c. So let's consider the parabola defined by the quadratic function here, f of x is equal to ax squared plus bx plus c. It turns out that there's a very simple formula for finding the vertex, the turning point. So I just want to stop here and say the vertex is the most important point. Okay, that turning point. So the parabola's vertex will, if you're in this form, ax squared plus bx plus c, okay, always, 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 all right? The vertex, the parabola's vertex, okay, is going to occur at the point negative b over 2a. That's the x-coordinate, so you can see the x-coordinate is negative b over 2a. And then to find the y-coordinate, you just plug it in. So f of negative b over 2a. So I'll write that here. The y-coordinate is f of negative b over 2a. Okay, so again, this y-coordinate is found by substituting the x-coordinate into the parabola's equation and evaluating the function at this value x. It's like just an amazing formula that you'll use and be like, oh, okay, so what's the vertex? Boom, boom, boom. I'll just plug this right in and go. And I'm going to do 2 examples so that you can see this, okay? So if you want to graph, okay, a quadratic function in this form, okay, not the standard form, okay, that's this ax squared plus bx plus c, so not in standard form. Okay. First thing you're going to do, again, is you're going to determine whether the parabola opens upward or downward. So again, you're just going to look at the value of a there. Okay, that's literally the most important part here. Okay, find the value. If a is positive, it's greater than 0, it's going to open upward. If a is negative, it's going to open downward. So you're going to use the formula to determine the vertex of the parabola. Okay, so you're just using formula on previous slide. So this is going to be the xy coordinate. So that's the vertex, this h comma k. Next thing you're going to do is you're going to find any intercepts by solving f of x is equal to 0. Okay, so just like I did before. So the real solutions again of this are the x-intercepts. I'll do examples so that you can see this. Again, you're going to find the y-intercept. Okay. Same way you did before, take 0, plug it in, and then you're going to plot all the intercepts you find, the vertex, and any additional points as necessary. Okay, so what I have next for us is I have 2 examples here. Okay, the first one's going to be pretty straightforward, pretty easy, and then the second one's going to be a little bit more arduous, involve a little bit more work, but that's okay. Okay, so let's do this. Let's graph the quadratic function f of x is equal to x squared plus x minus 6. Okay, so the first thing you're going to do, 1. So just so we're clear here, this is so my value of a is what is in front here, so it's 1. My value of b is also a 1. And my value of c here, is negative 6. All right, so opens upward or downward? Well, look here. Look at the value of a. A is positive. The function, the parabola, opens upward. Next, you need the vertex. Okay. And so we're going to use this formula right here, negative b over 2a. Okay. So the x value is negative b over 2a. All right, so it gets a little tricky here, okay? So it's negative b, so it's negative 1 over 2 times 1. So this is negative 1/2, okay? So just so we're clear here, this is the x coordinate. So to find the y coordinate, there'd be a little bit of work here, okay? It's a little bit tricky, okay? You're going to need to solve f of negative 1/2. So this is going to involve working with fractions, okay? So it's just plugging it in. It's negative 1/2 squared plus negative 1/2 minus 6. Okay? So just be careful here. Okay? What is negative 1/2 squared? That's 1/4 minus 1/2 minus 6. Okay, so you can just find, take care of the fractions first, you can even find the common denominator, right? Common denominator is 4. So it's 1/4 minus 2/4. Okay, and put this over 4 is minus 24/4. Okay, so this becomes, just so we're clear here, so this is 1 minus 1 minus 2 is minus 1, so this becomes minus 25 over 4. Okay, so just be careful. So this is just a little bit more than 6, just a little bit more than 6. Okay, so you can even grab a calculator here and round it to 2 decimal points if it helps to see this. So take 25 divided by 4 and you get 6.25. Okay, so the vertex is the point negative 1/2 comma negative 25 over 4. Or if you just want to see it as a decimal, it's negative 0.5 comma negative 6.25. All right, whew, a lot of not so easy with fractions, but that's okay. So find the x-intercepts by solving f of x is equal to 0. Okay, so let's do that. So you're going to solve. So you get x squared plus x minus 6 is equal to 0. You can see that this easily factors, right? Two numbers that multiply to negative 6 sum to 1. So this is going to factor into x plus 3 times x minus 2 is equal to 0. And you can see here you either get x plus 3 is equal to 0 or x minus 2 is equal to 0. So the x-intercepts are going to occur at negative 3 and 2. Y-intercept. What's really awesome about this is when you go to find f of 0, it's just 0 squared plus 0 minus 6. It's always just the c value, okay? All right, so now, finally, Plot the points and smooth curve. Okay, so let's do the y-intercept because it's right here. Okay, it's 0, -6, so it's way down here. The x-intercept is -3, and then 2. And then the vertex, just going back, is -1/2, and this is gonna be eyeballed a lot here. -1/2, and then -6.25. So here's -1/2 right here, and 6.25 is roughly right here. And then you can see, just recall, there's a mirror reflection of this point right over here. And then just a smooth curve through. And we got it. Vertex intercepts, and then you got the, I like doing the mirror reflection of the y intercept. It's just easy to even eyeball and see it using the axis of symmetry. But there you go. You got 5 points to just draw the curve right through it. Okay. So let's do this one here. Okay, this is a little bit harder. All right, so let's graph the quadratic function f of x is equal to -x squared plus 4x plus 1. Okay, so just so we're clear here, looking at this, my value of a is -1, my value of b is 4, and my value of c is 1. All right, so I have these steps worked out here just to save a little bit of time for this, but determine how the parabola opens. Well, look, a is -1, so that's less than 0, so the parabola is going to open downward. So you can see here that even off to the side here, we have in the slides, we said, okay, look, in the previous example, we said it was going to open upward because a was greater than 0. So, I knew off the bat it was going to look like this. And you can see I have that. So now this one here, when I go to sketch this, it's going to be downward. Okay, so we're going to find the vertex. Okay, so use this formula. So the x-coordinate of the vertex is -b over 2a. So that's -b, so that's -4, over 2 times a. Well, 2 times a here is -1. So this really becomes -4 over -2. The negatives cancel, and the x-coordinate is 2. Okay, so to find the y-coordinate, we plug this in. And so you can see that here, just to save a little bit of time, when we take this and plug this into the function, okay, you get -2 squared, negative, and then 2 squared plus 4 times 2 plus 1. It ends up being 5. So this is the y-coordinate. And you can see here the coordinate of the vertex is just 2, 5. That's it. Boom, we got it. All right, so next to find the x-intercept. So this is a bit tricky, okay? And this is why I wrote this out here. So when you set this equal to 0, so 0 is equal to -x squared plus 4x plus 1. It doesn't factor. So one of the easiest things to do is just use the quadratic formula to solve. And here what we're doing is we're rounding to 1 decimal place here. And I'm not going to walk you through this, in much detail here. I'll let you, pause the video or on your own verify this. But if you use the quadratic formula to solve here, you're going to get two solutions, right? Because the quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. This right here. So this plus or minus tells me there's two solutions. So I see here that the x coordinates here of the x-intercepts are negative 0.2 and 4.2. And remember, the y value at the x-intercept is 0. So we get two x-intercepts here. One at negative 0.2 and the other value at 4.2. Finding the y-intercept is very easy. You just plug 0 into the function and you're really just left with that c value. So the y-intercept is 0, 1. And then look, now you're ready to plot this, okay? So the first things you're going to do, right? You're going to plot the x-intercepts right here. Then you're going to plot the y-intercept right there. And then you're going to plot the vertex. Right? And you can see here that you can just draw a nice smooth curve through it. All right? And you can even label here the axis of symmetry is labeled here. I'm going to call it AOS, axis of symmetry, right there at x is equal to 2. So at the x value of the vertex. So we've done two examples here, one that involved fraction and one involved using the quadratic formula. And in both cases, I don't think the work here is too hard. What's hard is, there's a lot of steps, and if you're not meticulous in your work, it's very easy to make one little mistake and it'll throw off your whole problem. So just be meticulous and take your time. Okay. Now I want to talk about maximum, minimum. Okay, so if you have a quadratic function, okay, the maximum and minimum value of the quadratic function is going to occur at the vertex, okay? Okay, that's easy. Like, we know how to find the vertex. So consider the quadratic function f of x is equal to ax squared plus bx plus c. If a is greater than 0, then f has a minimum, which occurs at x is equal to negative b over 2a. The minimum value is this f of negative b over 2a. So if you look here, if we know that a is greater than 0, we know the parabola opens upward. So this vertex here has to be the minimum value here. This is where the min occurs. Okay, the flip side here is if a is less than 0, okay, then f has a maximum, okay, that occurs at the vertex. So at x is equal to negative b over 2a, and this maximum value is f of negative b over 2a. So the reason being here is if you know it opens downward, like so. This vertex here is where the max occurs. All right, so in each case, the value of x is equal to negative b over 2a gives the location of the maximum minimum value, and the value y, or f of negative b over 2a, gives the minimum or maximum value. Okay, and just so we're here, the sign of a tells if it is a max or min. Okay, just right off the bat, the sign of a here tells if it's a max or min value. All right, so let's try this case here. All right, let's consider this quadratic function. F of x is equal to 4x squared minus 16x plus 1,000. Okay, determine without graphing whether the function has a minimum or maximum value. All right, well look. You're going to look at the value of a. All right, it's equal to 4. It's greater than 0. Okay, so going back, if a is greater than 0, it has a minimum value. So this function has a minimum value. Okay, the reason being is if you were to sketch this graph, and this is without graphing, but I'm going to just show you here, okay? It's going to open upward, So the vertex has to be a minimum. Next, find the maximum and minimum value and determine where it occurs. So you're just going to use this negative b over 2a to find the x coordinate. Okay, so first you're going to find the x coordinate. So just, negative b, so my b is negative 16, so negative is going to be 16. Divided by 2a, well, that's 2 times 4, that's 8. So that's 2. Then you're going to find the y coordinate. So you're going to take this and plug it in. Okay, so you're going to plug in f of 2. Okay, plug in 2 to get f of 2 here. And then when you do that, here, I'll just save us a little time. If you were to plug 2 and chug through this, you'd get 984. So what we're saying here then is the minimum value of the function is this, okay? And it occurs at x is equal to 2. So just so we're clear, the y value here is the minimum value. So if a question says, what is the minimum value? Don't put the coordinate, you just put the y value. And then it'll ask you where it occurs, then you would put at x is equal to 2. What's really cool from this is now we can identify the function's domain and range. And so for all quadratic function, the domain is all real numbers, okay? So it's from negative infinity to infinity. So we found the vertex. Okay, so the vertex is the point 2, 984. Since a is greater than 0, the function has a minimum value at the vertex, so it's going to open up. So the range is actually going to be from 984 because this is the minimum value. Okay, function cannot have a lower value. And it's going to go to infinity. So we were able to determine the domain. The domain of a quadratic function is always all real numbers. Okay, and the range here is going to be 984 to infinity. And now what's interesting, if it has a maximum value, so suppose the max had been 948, it would have been negative infinity to 984. I think I said 948, but 984. All right. Now let's end by doing a word problem. Okay, so this is talking about strategies for solving problems involving maximum and minimum quadratic functions. So these can be a bit tricky. So the first thing you're going to do is you're going to read the problem carefully and decide which quantity is being maximized or minimized. Okay, so the problem I have next will say, maximize the area. So okay, so I want to find a max somehow. Okay, or maybe it's minimized, forgive me. Maximum, nope, max. Okay, so use the conditions of the problem to express the quantity as a function of one variable. Now this is tricky, okay? When you do these problems, you actually might need to define two equations. Okay, it's a bit tricky, okay? And sub one equation into the other. All right, I'll show you how to do that in the first example. The next thing you're going to do is you're going to rewrite the function in this form. F of x is equal to ax squared plus bx plus c. Okay. Then you're going to calculate negative b over 2a. All right, if a is greater than 0, obviously you're going to have a minimum value at this x with a minimum value of f of negative b over 2a. If a is less than 0, f has a maximum, okay, at x is equal to negative b over 2a, and this maximum value is f of negative b over 2a. And then you're just going to answer, you're going to take your values and figure out how, put them into the context of the problem. You're going to answer the question posed in the problem. All right, so here's the problem. You have 120 feet of fencing, okay, to enclose a rectangular region. Okay, so you have this rectangular region. So think about this. You have a length and you have a width. Find the dimensions of the rectangle that maximize the enclosed area. Okay, and then find what is the maximum area. Okay, so step one, decide what is being maximized or minimized. Well, look, it's right here. Maximize area. So we must maximize the area. So think about the area. What is the area of a rectangle? It's length times width. Well, here's the thing. You don't know what the length and the width is, right? Like, I don't know. So I'm going to set length equal to the x, and width is going to be a different variable, y. Okay, so area here is equal to x times y. But what do I know? I have 120 feet of fencing. So that's the total perimeter. So notice how, like here, I'm trying to maximize the area, right? But it's an equation of two variables. But we know perimeter is 2 times the length plus 2 times the width. So 2x plus 2y is equal to 120. So now watch what I do next here. Okay, so we must maximize the area of the rectangle here. Okay, so this is what I said. Area is equal to x times y, but this is two variables. We have 120 feet of fencing, so the perimeter of the rectangle is 120. So look, 2x plus 2i is equal to 120. This, you can actually think, this might be our constraint equation. Okay, this is the constraint we apply on maximizing the area, right? Because if you're like, oh, just maximize the area, well then, you know, I would have the fence be an infinite length times an infinite width. So it doesn't, you need some type of constraint. So you're going to take this constraint equation and solve for y. Okay, so you're going to get y by itself. So you subtract the 2x over, you divide by 2, and look, it's just 60 minus x. So now what you're going to do is you're going to sub this in for y. So I'm going to move, actually put it over here. Y is equal to 60 minus x. Substitute in our equation we are trying to max. So now the area is equal to x times 60 minus x. When I distribute the x, wow, look at this. I get it as a quadratic function here. So just rearranging it, I get it as negative x squared plus 60 minus x. So our area is now a function of x, actually. This is awesome. And now we can go through and figure out max and min. All right, so write it in function form. So ax is equal to negative x squared plus 60. So calculate, you got to find the vertex, okay? Okay, so going back here, I missed. So we've written it as a function form. Now we got to find this max min here. All right, so find the vertex. So the x coordinate of the vertex is negative b over 2a. Well, look, my b here and my a here is equal to negative 1. So x is equal to, it ends up being negative 60 over 2 times negative 1, which ends up just being 30. Then look at this. Since a is less than 0, the function has a maximum value. Okay, so going back here, this is what's awesome. We're able to figure out that the length here must be 30. And you can actually even figure out the y, right? Y is 60 minus x, so 60 minus 30. So it's a 30 by 30 here. It's actually a square, but squares are rectangles too, so it's all good. So this means that the area A of x of the rectangle with perimeter 120 feet is a maximum when the rectangle's dimension x is 30 feet. So answer the question posed. The last question was, going back, what is the maximum area? So to find area, well, we have an area function just as x. So the rectangle that gives the maximum area has dimensions 30 by 30, as I said. And so just take 30 and plug it into my area function. So my area function was minus x squared plus 60x. If you plug 30 in here, you just get 900. So the maximum area is 900 square feet. All right, so I know these last problems are a bit tricky, but the way you tackle them is you're most likely going to need two equations. You're going to need this what I call this constraint equation, and you plug it into whatever equation you're trying to maximize or minimize.